Okay, hey there everybody, it's Mr. Sheenline. This is pretty much notes for if you were absent, I guess if you were absent, because we did these notes in class. So this video is going to be covering Unit 3.1 Part 2 notes. So, ionic bonds. So the previous notes that we went through, the previous, from yesterday, well, it would have been yesterday, at your at-home learning day, you would have gone through, the Lewis dot diagram, valence electrons, all that good stuff. Now we're going to be taking the valence electron material, and we're going to be talking about how we can use that information. Use that information in order to, depict what's happening in certain bonds, specifically ionic bonds more than anything. Okay, so let's just get right to it. So, the first thing we need to identify and what we need to know about are cations. So, cations are positively charged ions. There's a great little way that you can know which is which, what kind of ion is which kind of ion. You should always think cations are positive. Haha. Oh my goodness, it's too funny. My stomach hurts too much. My belly hurts too much from you laughing. Oh my God, amazing. It's great. It took me years to develop this joke. Thank you. I'm selling the rights and they're making a movie. But anyway. So you've got cations and anions. Cations are positive. Anions are negatively charged ions. Okay? So remember, ions are just atoms that have lost or gained electrons. So if they've lost electrons, they're going to be positively charged ions. If they've gained electrons, they're going to be negatively charged ions. Because remember, electrons are negatively charged particles. So if you gain more, you're going to have a negative charge. If you lose them, you're going to have a positive charge. Okay? And we have to know that because we have to know what an ionic bond is. An ionic bond is a bond formed when atoms gain or lose electrons in order to become stable with a full valence electron shell or level. So atoms want to become stable. And if an atom somehow becomes an ion, it's freaking out. It's like, oh my God, I just want to, or when it's exposed, to something else. Oh my goodness, what? I'm burping and hiccuping and yawning. I am so sorry. When they are exposed to another particular kind of element, they are going to be more inclined to either be giving away or gaining, taking these electrons. So, but what's important here is that bonds are formed when atoms gain or lose electrons. So, in ionic bonds, one atom is going to more or less steal elements from another, okay? While on the flip side of things, one atom is going to just be like, just get rid of this atom. Get rid of these electrons. Get rid of these two electrons. I don't want them anymore. Just get rid of them. They're weighing me down, and I want to reach a point to where I don't have to carry this dead weight, okay? So that is an ionic bond. Okay, and the ionic bonds are going to be between cations and anions. So typically, this is the bonding of a metal and a non-metal. Typically, when we're practicing in class, it'll be pretty much always a non-metal with a metal. Okay, or so I should say in the proper order, a metal with a non-metal. When we write these out, we always write the cation first, and the cation, for the most part, is always the metal, and the anion second, and the anion is pretty much always going to be the non-metal, okay, as I've got it written here. Okay. All right. So the properties of ionically bonded material. So typically, ionically bonded material, they're going to be brittle when they're solids, which for the most part makes sense. If you think of iron oxide, think of iron oxide. It's a great example. Iron oxide's rust. So when you leave iron outside for a while, it's that orange tingy color. That iron has reacted to that oxygen it's changed its chemical properties. It's a different thing, and that thing just happens to be iron oxide, and it's super crusty, and it's thin, it's powdery, it's chips away. Not much you can do about it. Okay. Easily soluble, meaning that it dissolves pretty easily in water. So like this next one disassociates in water pretty easily, breaks apart into its ions. And just so you know, it's not H in the it's not H20 that is supposed to be this. It's supposed to be H subscript 2 and then O, so water. As a liquid or solution, it's a good conductor of electricity, which would make sense because it's a metal with a nonmetal. Okay, so that metal material in there, that's going to act as a pretty good conductor. And of course, again, because a good chunk of it's going to be metal, it'll have a high melting point. Okay, so it'll have the threshold to turn it from a solid to a liquid is a pretty high temperature. Okay. Now we don't need to really know this or at least we really have to study this hard. This labeling as a formula unit. Just you need to know that or be familiar with this word because it's going to be coming up a lot when we get into material in the in like Unit 4 and especially in second semester, especially in the second semester. But anyway, when we write formulas out, so this is a separate idea. When we write the formulas of ionically bonded compounds out, we use what's referred to as an empirical formula. So an empirical formula uses the lowest whole number ratio of atoms in a compound. So when we bond, let's say sodium together, there's one sodium atom, one chlorine atom. It's 1 to 1. So we just write it 1 to 1. We don't write it, Na2Cl2. It's redundant, it's ridiculous, and it's incorrect. We just write it to the lowest, as it says here, the lowest whole number ratio. Okay. So this is where we tie it into the Lewis dot structure right here. Let's kind of take a look at NaCl with sodium chloride. So ionic bonds would be like this. So if we've got sodium here, and if we look on the periodic table, sodium is going to have just one. It's going to have just one valence electron, and then there's going to be chlorine over here, and chlorine is in the 7A group, and chlorine happens to have 7 valence electrons. So you tell me, who wants to give up what? Do you think it's going to be easier to give up 1 electron, or is it going to be easier to take 1 electron? I think you understand what, the answer there. So it would be like this. So an ionic bond would be chlorine more or less stealing this electron. So chlorine here would more or less just say, yep, this is mine. Thank you. While sodium over here just kind of does its own thing, and he's just like, oh, okay, this is fine. This is okay. It's like I don't have this dead weight anymore. I can just kind of do my own. Well, I can't do my own thing, but at least I have a friend here that took this weight off my shoulders. Because here, chlorine has now completed its outer shell here, its outer valence electron shell. The octet rule has been met, and it's happy as a clam. Same thing with sodium here. Sodium now it doesn't have to worry about extra electrons on its outer shell. It doesn't have any anymore because chlorine took it off its hands. So he's happy. Chlorine's happy. We're all good. But the point being is that in an ionic bond, one ion is going to gain, the other is going to give up. Okay, that's the main point because it's pretty different from a covalent bond. So let's maybe take a look at covalent bonds then. So in a covalent bond, bonds are formed when atoms share electrons. So the key word here is share electrons. And we know that because it's a covalent. It's a covalent bond. So think of it, listen to that word, co and then valent. Valent as in valence electrons. Well, yeah, valence electrons, and then co as in cooperative. Come on, it's too easy to not forget, okay? Or at least it should be. So when you hear covalent, you should think cooperation, you should think co-op, you should not co-op as in someone more or less usurping someone else, more of co-op like cooperation, collaboration. Okay, so they're going to be sharing the electrons. Now, typically, this is bonding two or more nonmetals together. Okay, so understand these differences. So covalent, oh boy, covalent is two or more nonmetals. Ionic is bonding metals and nonmetals. Okay, notice the difference. Memorize the difference. So then the properties of covalent bonds. Covalent bonds are just more malleable as solids, which again, that makes sense because we're not dealing with metals anymore, we're dealing with nonmetals. So then they're somewhat soluble, which means that they're not going to dissociate terribly well in water. They're going to be sticking together pretty hard, which also makes sense because they're sharing electrons, so the bond's going to be tougher. It's going to be much more harder to break. They're not good conductors of electricity when in a solution or as a liquid, which again, well, that makes sense because again, they'll have metalloids. You know, maybe two metalloids or a metalloid and a nonmetal will bond together. But no, that makes sense. There's not a metal in here. And then lower melting point again, because there's no metal in here. That means that it has that the temperature needed to go from a solid to a liquid or a liquid to a solid is not as high. It's decently low. Okay. And then on the back, labeled as molecules. So again, this is the same thing as the formula units for ionic bonds. For ionic compounds, we refer to covalently bonded compounds as molecules. Okay, this is more. We're going to apply this further and more in Unit 4 and further on in the second semester. Okay. And then the way we write their formulas, write their formulas as a molecular formula. So it shows both types and the numbers of atoms making up the molecule. So we use the actual number of atoms being used inside of the molecule. So glucose is a good example here. So C6H12O6. If you were to see the big old molecule just floating around, you would see 6 carbon, 12 hydrogen, and 6 oxygen. Okay, because if we were to write this in an empirical way, it would be CH2O. Okay, and we don't want to do that because we want to accurately represent the number of atoms found in this molecule. Another good example would be like water. So water is also a covalently bonded molecule, and water is there's 2 hydrogen and 1 oxygen because we know that with the 1 oxygen here, which when bonded will look like this. 1, 2, 3, 4, and let's see. Well, I messed up. Shoot, I messed up the whatchamacallits. Messed up my number of. Got ahead of myself and messed up the number. Just 1, 1. So this is how we would draw a water molecule using the Lewis dot structure to show all of our different valence electrons and how they bond. But like a good example here is you've got one oxygen and 2 hydrogen. Okay, you have 1 oxygen and 2 hydrogen here. And because that's what you find in every molecule of water, there's 2 hydrogen and 1 oxygen. Okay. Now let's tie this into the idea that they share the electrons. Because remember, ionic, 1 steals, 1 gives away. Covalent, they just share. So in water, this hydrogen is going to share his electron with oxygen here, and the oxygen is going to share his electron with hydrogen here, because hydrogen, only having 1 in its first shell, it would like to have 2. Okay, it would like to complete that outer shell, because remember, it only has 1 shell, and it can only hold 2 in that first shell. So it would like to have 2. So it's going to just share. He's going to be like, oh yeah, let's just you can have it for some time, and I'll borrow yours, and then we'll switch back and forth, man. And the same thing applies to this guy over here. It's going to share his electron And then with oxygen will do the same. Because notice, oxygen doesn't lose here because oxygen gets to then share 2 electrons from the 2 hydrogen, thus completing its outer shell. So then it's fine with having an 8. The octet rule is complete. Okay? So again, covalent bonding, covalent bond sharing, ionic bond stealing or giving away. Okay? All right, so those are the notes for the bond types. One last little diddly. So now I would get out your periodic table because we're going to have to do some coloring. So real quick. So in order to, sorry if I just blasted your ears with that, but what we have to do is we've got to associate we've got to associate the elements of the periodic table with the type of elements that they are actually, or what they are. Oh my goodness, let me rephrase that. We have to identify each element by its type. So all the pink here are metals. So, and I've got my key up here. So all the pink are metals, all the green are metalloids, all the yellow are nonmetals. So color in. Notice that it's lithium and beryllium right here. Color in all this. And here, I'll zoom in to show you where that cuts off at. It's hard to see. So again, all of this are metals. All these guys down here, metals. Here, I'll zoom in. Oop. I'll zoom in over here, show you where it splits. So again, the green is metalloids. Hydrogen's also a nonmetal, by the way, if you didn't notice that. Hydrogen's a nonmetal. The metalloids will all be green. Okay. And then all the nonmetals are going to be yellow. Okay, so I'd pause this video here. I'll put this in the center again. I'd pause the video, take a peek at this, okay, and color it the way I've got it colored here. Okay, so pause the video here, color it in, and then start playing it again. Okay, so the last idea, after you've got this all colored in, the last idea I have for you, when we are working with ionic bonds and in this, and you will be using this. Like this is very, very valuable here because you will be given, as you'll see in the next notes, you'll be just thrown material, and you've got to determine if you've got is that the anion or is that the cation, and this will definitely help you. Just know that if you are given a metal in an ionic bond, if you have a metalloid, so if you're given boron or silicon or germanium or arsenic, actinium, tellurium, polonium, or astatine, if you're provided these elements, you're going to treat these guys as nonmetals. Okay, just to keep things simple inside the classroom. Anytime that there's an example with these guys provided, these metalloids, you're going to just treat them as nonmetals. Okay, it's not terribly often. Boron comes in every now and again. Silicon comes in every now and again, and I think so does arsenic. But for the most part, and so does antimony, but that's later on. But anyway, like it'll be very obvious. Like I'll just let you know, it'll be very obvious if it's if it's an ionic bond or a covalent bond. Also. It's very possible that these nonmetals will, in covalent bonds, these nonmetals will sometimes will be paired up with these metalloids, I should say, will be paired up with nonmetals. Again, we'll treat them as nonmetals. So just fast rule: anytime we find an example of a metalloid, just treat it as a nonmetal. Easy peasy. Okay. All right. Well, that's all I have for you guys. If you have any questions, make sure you ask me. If not, well, then I'll see you in the next one.